Okay, so welcome to Lecture 3 of Introduction to Quantum Computation at Paderborn University. I hope you guys had a good weekend. It was a long weekend here in Germany. May 1st is a holiday for us. Today we're talking about measurement, okay, which is the fourth postulate of quantum mechanics. Okay, last lecture we did the first three postulates, and now we're going to do measurement. And as a result, we can do our first application of some quantum communication task, quantum teleportation. Before we get into the lecture at all, let me just briefly state some announcements. So assignment 1 hand-in seems to have gone successfully on Panda, so thank you for doing that. Assignment 3 should be up soon, and tutorials should begin in theory starting this week. And I will have to figure out how exactly we're going to do that, because normally it's an interactive thing. Of course, we do in class. I get you guys to answer the questions on the board, so obviously we cannot do that in this format. So let me think a little bit about how we want to proceed with that. There were a few suggestions last week, third one here. There were a few suggestions last week to write with a thicker pen so that maybe it's a bit easier to see online. So I've done that. You know, it was very easy. Thank you for bugging me for that. If there are any other suggestions, I'm happy to consider them. Okay, so this in particular was super easy to do. Okay, so with that said, let's start lecture 3. Okay, so lecture 3 again is about measurements, and it's going to be one of the postulates of quantum mechanics that really differentiates it from the world of classical mechanics that you and I are most familiar with. Okay, so there are two quotes atop this one, and the quotes together tell a story, right? The first quote atop the lecture notes is by Albert Einstein, and it says, "I think that a particle must have a separate reality independent of measurements. That is, an electron has spin, location, and so forth, even when it's not being measured. I like to think the moon is there, even if I'm not looking at it." Okay, so here Einstein is talking about this idea that, you know, the concept of an object, or the existence of an object, is not dependent on our measurement of the object in some sense, okay? That it objectively just exists independent of us, right? And later on, David Mermin makes this quote, which says that experiments have now shown that what bothered Einstein is not a debatable point, but the observed behavior of the real world. Okay, so these two quotes are really showing a bit of the progression of, you know, the thinking of quantum mechanics through the ages, if you will, or really it's been just a century, or through the decades, right? And today we'll be talking about the measurement postulate, which is really very much what these quotes are about. And the idea is as follows, right? I mean, so far everything we've done, you might think it's everything you need to do computation, right? I mean, classically, at least, these are the main things we worry about, which are, you know, how do we represent states in our computer? What kind of gates can we apply on them? And in particular, how do we represent composite systems? Okay, so multiple bits at a time, right? And so classically, we just take it for granted that, you know, when your computation is over, say you factored your numbers, and you're going to pull out the answer, we take that last step of reading out the answer for granted, okay? We leave that to the engineers. And quantumly, that's highly, highly non-trivial, okay? This last step is what we refer to as measurement. That's what the entire lecture today is devoted to, okay? Okay, and of course, what's going to happen here is that, as these quotes at the beginning of the lecture foreshadow, the idea of measurement is again going to proceed not as expected. The very act of measuring an object will seem to change the reality, or the state of the object, right? And that's exactly what Einstein was not so happy about, right? Like, how could it be that, you know, my act of looking at the moon can cause it to exist or not exist, or could change its state? Okay, and that's what we're going to see today, that measurement causes objects, quantum objects, at least according to the laws of quantum mechanics, if you believe them literally. It causes them to change their state. Okay? And, you know, remember, or well, I don't really know if I stated this at any point, but let me say, you know, one of the ways you can think about this idea that quantum measurements can change the state of an object is this idea that, you know, quantum objects, you know, and this is very much a hand-wavy opinion that I hold. This is not necessarily a fact by any means, but at least it helps me internalize, you know, why in the world should quantum measurements change the state of a quantum state? And the intuitive idea is that, you know, quantum objects are tiny, right? We're talking about subatomic particles, right? Like electrons, let's say. And, well, how do you observe, say, an electron or some other object? Well, you have to interact with it somehow, right? And one way of interacting, for example, is maybe you shine like some sort of light or a laser on this object. And And that bounces back to your eyes, and then your brain processes that what the photons, the incoming photons, and produces an image, right? That's the act of the measurement. But when you bombard something with photons, like a laser beam, for example, those photons are hitting this object, right? This electron, and the electron is so tiny that just the mere act of hitting it with these photons is going to disturb the state of that electron somehow, right? At least that's an intuitive way of trying to reason with why it might be that quantum measurements should disturb an object. Okay, now, of course, this is a mathematical course. We want to model what we mean by measurement. And in order to do that, we're going to have to talk about, I'm going to have to formalize 3 classes of operators: Hermitian, positive semi-definite, and orthogonal projection operators. And each of these operators will start most general and will get more and more precise, or we'll go to smaller and smaller classes, right? Each of which is contained in the previous class. And as we'll see, these are basically going to be nothing other than high-dimensional generalizations of the numbers you and I kind of know and love, like the real numbers will generalize to the Hermitian operators. The non-negative real numbers will generalize to positive semi-definite operators. And finally, bits will generalize to orthogonal projection operators. Okay, so let me start by telling you about, let me write the title first. So, of course, we're talking about postulate 4, measurement. Oops, did not work well. All right. So the 3 types of operators we'll deal with in this course, okay, so it's not just for measurement, 3 classes of operators, or matrices. We're going to start with, let's start with the Hermitian operators. Okay. Oops, let's do that in blue. Okay, so a Hermitian operator, normally the way I like to present this is I like to first give you the definition of a Hermitian operator, but this time I'm going to go backwards. Okay, I'm going to actually show you how you get these operators just by generalizing the corresponding class of real numbers, okay, because that's really what you should think of these as, right? So Hermitian operators are supposed to generalize, or maybe I should not say general, let me be more precise, they're kind of a high-dimensional analog of the real numbers. Okay, so what do I mean by that? So suppose you take your favorite real number r, right? And I can think of this thing as, so imagine r is a real number, I can think of this as a 1-by-1 matrix, right? And what is this? This is really just contained in, this is a subset of, it's contained in r 1-by-1, right? I can write it that way. So, but if to generalize this to high dimensions, there are multiple ways you can think of doing that. One way of doing is that I could instead take not just one real number, but I could take a number of real numbers and, say put them on the diagonal of some operator with zeros everywhere else. Okay. And now this is an operator in R 3-by-3. Okay, and now you can think of this as a high-dimensional analog of real numbers. It's one way you could generalize them. Okay. And indeed, it'll turn out that these guys are also Hermitian matrices. Again, I haven't defined Hermitian operators yet. Okay, so here we're talking about diagonal operators with real numbers on the diagonal, basically. And then, of course, it's not so interesting if I just take things and I embed them onto the diagonal, because, I might as well just have written the numbers in a list. What's with all the zeros? But of course, now I'm working in the matrix space, so I can change the basis in which I represent the matrix. And that means I can conjugate the matrix by a unitary operator. Okay, so let's do that, right? So not only that, but I could take, well, maybe a nicer way of doing it is I could just, let me just erase this thing. And I can take my favorite unitary operator, take a unitary U, and now this thing acts on the space of all unitary operators, which takes C3 back to itself, right? And if I take this thing and I conjugate it, this matrix, and I conjugate it with U, what it will do is it will no longer look diagonal in the standard basis. It's basically rotated the base in which this matrix is represented. But the point is that, sitting here, remember from previous lessons that it's a diagonal matrix, so the eigenvalues are sitting on the diagonal of this matrix. They're all real, okay? And when I apply unitary, it doesn't change the eigenvalues, right? So the eigenvalues are still real. Okay, so in this sense, Hermitian operators are going to be operators which we can diagonalize, right? And whose eigenvalues are all going to be real. Okay? So let's give the formal definition, right? I mean, so that's the intuition, and you can kind of recover that from the formal definition. The formal definition is the following: that if I have an operator M, and it's a linear operator, it takes CD to itself. This is Hermitian if M dagger equals M. Okay, so if you take the transpose and the entropized conjugate transpose, so the transpose and the complex conjugate entry-wise, you get the matrix back. Okay? So that's just the plain vanilla definition. Okay? So if all the entries are real, in particular here, we're just talking about symmetric matrices. Okay? So, examples of these that you've already seen are, in fact, Pauli x, y, z. Right? So remember that x looks like this. Okay, so it's real, and certainly it's symmetric. If you take the transpose, you get the same thing back. So not only is x unitary like we saw, it's actually Hermitian. Okay, so it's a bit stronger. And of course, because it's unitary, remember we said that x was, not because it's unitary, but we said that x is self-inverse. And indeed here we see that, right? The inverse of a unitary matrix is M dagger, and x is Hermitian. So indeed, it's going to be self-inverse. The matrix itself equals to its dagger, which is its inverse, in the case of Pauli x. Okay? Okay, so Hermitian operators, from this you can extract this property that they're going to be diagonalizable. And why is that? Well, because they're normal. Remember we defined normal, like this means something, right? Normal meant that M dagger equals to M dagger M. So I'll leave it to you to just piece together, this property to clearly see that this holds. And what you can prove is that their eigenvalues are real. Okay, in this sense, Hermitian operators will generalize the real numbers. Okay, now the next class I want to define are the positive semi-definite operators. Positive semi-definite. Okay, and a lot of times, obviously that's a mouthful. Nobody wants to say positive semi-definite, so we just say PSD typically. Okay, so positive semi-definite numbers are, if we go back to this example over here, right? Here I said these diagonal numbers were all real numbers, so we got the Hermitian operators. Now if I change the eigenvalues to be non-negative real numbers, so I restrict them further to the right half of the real line, including the origin, right? Then you get the PSD operators, the positive semi-definite operators. Okay, so these are basically going to be Hermitian operators. So it's a subclass, so I might as well just start with that definition. With non-negative, so let me be clear here. Non-negative eigenvalues. Okay. And so in this sense, they generalize the non-negative real numbers. Okay. So otherwise, everything is the exact same for Hermitian operator. Okay, so certainly they're going to be Hermitian. It's just that the eigenvalues will be non-negative. And there are some ways to, okay, so what I've told you right now is that the eigenvalues of a PSD operator are non-negative, right? And so that's one way to characterize PSD operators. It's not actually the original definition. An equivalent definition to this is that for all psi, and I believe this should be on your assignment, for all psi, the following holds. Okay, so, sorry, we're working in, say, CD. M is PSD if and only if psi M psi is greater than or equal to 0. Okay, so if you take your matrix M and you kind of bracket it with any vector psi, it doesn't matter what the norm of the vector is, it should always be non-negative, this quantity. Okay? One thing I will do is some notation here, right? So here I wrote PSD, it's much faster in general for me to do this, and this is standard notation in the field. Let me get rid of this, and instead from now on we'll write this, this kind of curly bracket greater than or equal to that, greater than or equal to. Okay, so this is generalized inequality, and so we've generalized it to apply to matrices now. Okay, Hermitian matrices in particular. Okay, so for any Hermitian matrix, if it has this, if I write it m is greater than or equal to 0, that means that its eigenvalues are all non-negative, and in particular, that means that it's PSD. Okay, and I believe that should be on your assignment to prove that, you know, these two characterizations of PSD operators are the same. And depending on the context, it might be more useful for you to think in terms of eigenvalues, or it might be more useful for you to think this way. Okay. Just a quick note. So here we're talking about, you know, non-negative eigenvalues, right? Or so this generalizes the non-negative real numbers. You might ask what happens if I talk about the strictly positive real numbers, and it's completely analogous. Then we might call it the set of positive definite operators. I'll put this in brackets. So there's no semi in front. It's just positive definite. And we might write PD for that. And these guys are the exact same definition. And so these are going to be Hermitian with positive evals. Okay, so strictly positive. And so you might ask yourself, you know, what happens to this condition? Right? How does this condition generalize, or how does it apply to this setting? I should not say generalize because it's a smaller class of operators now. And it's exactly what you expect. We say that M is now positive definite. You'll notice here that I did not put the equality part of this because it's strictly greater than 0. If and only if for all psi in CD, this expectation is now strictly greater than or equal to 0. Okay, so you'll notice how I'm missing the inequality. Okay, so sometimes in this course I'll talk about positive definite operators, and that's what I'm referring to. Okay, so all the eigenvalues, there are no 0 eigenvalues, and all the eigenvalues are strictly positive. Okay, so in particular this means, of course, that a positive definite operator does not have a null space, right? Its image is full dimensional. Okay, so one of the exercises, you know, which we'll do in the tutorial, but let me just state it, it's written in the notes, is that, you know, X, for example, Pauli X is not positive semi-definite. And, you know, there are various ways you can see this. You could go out and look up the spectral decomposition we came up with for X in a previous lecture. But, you know, potentially a faster way to do it is just to guess a vector. You know, you can guess a vector if you think about it long enough, guess some psi such that psi x psi is strictly smaller than 0, right? So it violates this criterion here. And so that as soon as you can guess such a psi, you immediately know that the operator x is not positive. Okay, and this is a really nice kind of life lesson, if you will, that, you know, using these different formalisms for defining the same properties, such as non-negative eigenvalues or, you know, non-negative expectation, depending on the situation, the one you use could make your life a lot easier. Okay, so in particular, you know, if x, you know, in this case, x is easy, it's just a 2x2 operator. But if I have a really large matrix, x, like it's exponentially large, m, you know, realistically, I probably won't be able to figure out its spectral decomposition. This thing is huge, right? But I might still be able to guess a vector of psi, such that this property holds. Okay, if I know enough about the structure of M, I might be able to do this. And then that would be my witness, my succinct witness in some sense that this operator, even though I can't diagonalize it fully, I know that it's at least not positive. Okay, so that's one of the scenarios in which it's actually more useful to use this characterization of being positive semi-definite. Okay, so far we talked about generalizations of non-negative real numbers, of real numbers, of non-negative real numbers, and of strictly positive numbers. And now, of course, we can really go all the way down to just bits 0 and 1. Okay, so here the right class of operators is called the orthogonal projection operators. Okay, and so these are what? Well, these are going to be Hermitian, okay, operators with eigenvalues in the set 0, 1. Okay, so that's one way to define it, basically. And of course, that means that these operators are positive semi-definite. Okay, in general, note that they won't be positive definite because you still are allowing a 0 eigenvalue. Okay, so formally, what is this equivalent to? Okay, we'll actually prove this equivalence now. So another way of stating this is that we'll say that Hermitian matrix pi. So often for projections, we'll talk about, we'll use the symbol pi. It's just fairly standard, I think, convention. A linear operator on CD is an orthogonal projector. Okay, or often we'll just say projector for short. If basically squaring it gives you the same operator back. Okay, so in other words, you might as well, if you repeat this operator over and over again, it has no further effect. The first time is everything. Okay, and I claim that, these two definitions are equivalent, right? That this property here is equivalent to having 0, 1 eigenvalues. Okay, so let's briefly prove this equivalence now. Okay, so maybe I should put 1 here and a 2, and so claim 1 is equivalent to 2. Okay, so let's do a proof of this. Okay, so how do we prove this? Well, obviously I'm talking about eigenvalues on the one hand, here they are. And on the other hand, I'm talking about this kind of algebraic property, pi squared equals pi, right? So again, the first thing you want to do for any proof, especially those involving eigenvalues, is you always want to think about the spectral decomposition, right? That's how you get at the eigenvalues, if you will. Okay, so let's take the spectral decomposition. So suppose we have a spectral decomposition pi equals to the sum over I of lambda I, like this. Okay. And now let's just use this equation that we have, right? So what I know is this, so let's just plug that in. Pi equals to pi squared, right? And on the left, what I can do is I can, plug in the spectral decomposition, right? Sum over I, ket bra lambda I, right? And on the right-hand side, I have, pi squared, so I have this spectral decomposition twice, right? Sum over I, lambda I, ket bra lambda I, sum over I, lambda I, ket bra lambda I. Okay? And now we multiply out, and remember that this is an orthonormal basis, right? This is an eigenbasis for this operator, so that means that even though I have, sorry, I should probably use a j here, even though I have two different indices here, whenever I take the inner product of lambda I and lambda j, unless the indices match, this thing's going to die off, right? So this is going to equal to what? It's going to be the sum over I. Let me be precise because this is still one of the first lectures, so let me just really write out everything step by step the first time just to remind you how this works. Okay, and remember this now is a scalar. Okay, and this equals to what? Well, this equals to lambda I, lambda j, and right, so where did this come from? Whoops, let's not do that. Okay, so this obviously becomes our Kronecker delta. Remember, Kronecker delta is 0 if the indices don't match and is 1 if the indices match. And that's exactly what you expect out of orthonormal basis. Okay, and so once the indices match, of course, I only have one term in the sum. And so I get lambda I squared, and then lambda I. Okay, so this is what I have now. Okay, and remember, so one of the most annoying things of getting the hang of quantum computing is not the actual math so much, but just the notation and how you're allowed to play with these things, right? And so that's why I'm taking the time to go through this example. So what we see now is on the left-hand side, you see that here you have sum over I, lambda I, and then, ket bra of that state. And this looks almost the same, right? Except I have the square over here. Okay, and so now we use the fact that, I have these operators here, these lambda i's, these are all, they come from an orthonormal basis, right? So the only way this equality can hold now, right? So this stands for because in this course, because the set here, because this is an orthonormal basis, remember ON meant orthonormal. So because this is an orthonormal basis, this implies that lambda I must equal to lambda I squared for all I. Okay, and there are d of them. Doesn't really matter, let's just index them this way, right? So this means that lambda I equals lambda I squared, and because we're working over the real numbers, right, these are Hermitian operators. Okay, so pi is Hermitian, right? So that meant that all the eigenvalues are real. Because we're working over the real numbers, there are only two real numbers that satisfy this equation, right? Those are going to be 0 and 1. Okay, so that's equivalent, right? So by the way, I should not say implies, this is really an equivalence. Okay, so the equality holds if and only if this is true, and that this is true if and only if this is true. Okay, so orthogonal projection operators have eigenvalues which are 0 and 1, and they're kind of the smallest class of Hermitian operators that we'll think about in this course for the most part. Okay, good. So let's just make a note. Okay, so we talked about three kinds of operators. Hermitian operators, right? Positive semi-definite operators and orthogonal projection operators. Generalizing the non-negative real numbers. The real numbers, the non-negative real numbers, and the numbers 0 and 1. And now let me make one last observation about projection operators, which will make our lives a lot easier. Because the eigenvalues of a projection operator are 0, 1, they always have the spectral decomposition, a very simple one, right? They always look like this. Pi equals the sum over I of eigenvectors lambda I, lambda I. Okay, so in particular, the eigenvalues are all 0 and 1, so I could really just, there's either a 1 or a 0 here. If there's 0, then obviously the term doesn't need to be written down, and if it's 1, then I don't need to write the 1 down. So anytime, it's just going to be a sum of orthonormal vectors, basically, and this turns out to be an equivalence, right? Okay, so in particular, the point here is for any orthonormal set, okay, it doesn't matter which one. So if I define pi this way, the sum over I of psi I is a projector. Okay, so that is an important fact we'll use throughout this course. It's one of the exercises in the notes, and I encourage you to do it. We'll probably end up doing it in the tutorial, taking it up in the tutorial. Okay, but if you follow this proof, it should be kind of straightforward to also do this as well. Okay, good. So let me say just a bit more about these projectors, right? So because I can write them this way, right? And in particular, if the projector is summing onto just a single term of a basis, well, just a single vector, a unit vector, right? Okay, so then we'd say the projector is rank 1, right? So here, what I want to say is that a projector pi has rank 1 if and only if pi equals to just take your unit vector for some, okay, whichever one you like, it doesn't really matter. Okay, and why is this? Just a hint. So the rank of pi in general will be is the number of non-zero eigenvalues, right? So because these things are diagonalizable, this tells you exactly what the rank is. Okay. Okay, so in particular then, if I just have one operator, I guess I didn't even need to put this I here, right? I could have just written psi. Right? So you're staring at the spectral decomposition of this thing, right? This is the only vector in the spectral decomposition of pi which has an eigenvalue of 1, and everything else is eigenvalue 0. Okay, so then the rank of this thing is 1. There's only one term in the spectral decomposition. Okay, so the last thing I want to say is, okay, so projectors generalize 0, 1, so what do they actually do for us? Like, why do we, geometrically, what is the intuition here? Right? And so a projector is, well, basically it's going to be the following, right? Let me draw a picture first. So intuitively, what this does is the following. If I have some vector, right, and it's sitting over here, okay, there's my vector psi. And I want to project onto an axis. Let's say I want to, let's suppose this is the standard basis in C2. If I want to project here onto this thing, that would be the same as projecting onto this. This is my projection operator, okay? And what it will do is it'll just basically look at the shadow, basically, right? It'll look at this vector here. That's what you'll get. That's the projection of psi onto the axis 0, right? And you'll notice first right away, I mean, no math required, right? Just your intuition will tell you that, notice how even if psi was a unit vector, pi of psi in general will not be a unit vector, right? We've cut off a certain component of psi, in particular, the direction here, the component along this direction has been eliminated. Okay, so later on we'll need to renormalize these things. Okay, so let's just mathematically, justify this idea that pi projects us onto, some state, okay, or some subspace more generally. So intuition. What does a projector do? Okay, so take any projector pi. Okay, I'm just going to imagine it projects onto some, not just a rank 1 subspace, but there can be more than one state psi I. And take any state phi to be measured. And I say this because ultimately this is what we're going to talk about today. Okay, so what is pi times phi? Let's just expand out the definition of pi, right? It's just sum over I, psi I, phi, right? And what happens now is I'm going to do this, right? Psi I of phi, right? Those come together. And again, these are just going to be a scalar now. And here I have this psi I, right? So here is, this is this state over here. This just comes over here, right? And this guy over here becomes my inner product, right? That's where that is. So it turns into a scalar. I could just move it in front now. Okay. And now what have I done now? You'll notice that what I have here is I've got a linear combination now of, the vectors psi I, the ones I'm projecting onto, plus some scalars right in front. So what that means is that, the state I started with, no matter what state phi I started with, the result of the projection now lives in a certain subspace, right? It's in the span of these guys, right? It's a combination of these guys. So it's in the span of the state psi I. Okay, and that's exactly what this picture does, right? In this picture, after the projection, I kill off the component that is not in this operator, right? This operator only cares about 0, 0, so when you do the projection, the component onto 1 is thrown out. Okay, and so projectors basically take your favorite vector and they push it down into some subspace. That's what they're doing. Okay, and in the most naive way possible, they just truncate everything that's not in the subspace. Okay, good. So now I've covered the types of operators we need to cover. And generally speaking, quantum states eventually, when we talk about density operators, they're going to be positive semi-definite operators. The types of measurements we'll focus on, however, are going to be even more restricted. They'll be the projective measurements. But again, there is a real sense, a formal, rigorous sense in which projective measurements are going to be, without loss of generality, the most general type of measurement you can do. Okay? But for now, let's just talk about projective measurements. We'll just assume that's the case. So projective measurements. Okay, so this is obviously why we wanted to define the notion of a projector. Okay, so what is a projective measurement? Okay, this is going to model our notion of a measurement of a quantum state. Okay, so it's going to be some set of projectors. Okay, so not just one projector now, but you get to pick a set of them. So I'll index them by I. Okay, and these could be acting on, maybe I'll just do it. So this set is just acting on some space CD, okay, a set of linear operators acting on CD. And there's one property that needs to hold, right? And the property we need to hold is that if I add these projectors, sum over I equals to 0 up to m, that should equal to the identity matrix. Okay, so this thing here has a special name. This thing is called the Completeness Relation. And we'll see why it's important in a second. It's without it, we don't have a proper measurement, basically. Okay, and so let me just make a note. Right, so like I said in this previous exercise, this pi doesn't have to project onto a one-dimensional space. It can project onto some larger subspace if you have multiple terms in the sum. But if you really have just one term in the sum, if this is just pi equals psi ket bra psi for just one psi, then it's a one-dimensional projection, right? And when this happens, we say that this measurement here, when all these pi i's are just rank 1, we say that we're measuring onto the basis that the pi i's are telling us. Okay, so if all pi I are rank 1, which means that all the pi I look like this. So they're just equal to a single vector for some unit vector. Of course, they're projectors. Then we say that the B basically, so B models a measurement. Okay, so let me just start introducing this notation. For short, this always means measurement in this course. Otherwise, we drive ourselves crazy writing all these letters. Oops, each time. Measurement. And we say it models a measurement in basis psi I. Okay, so if each of these pi i's are rank 1, then B itself as a set is modeling a measurement in that basis. Okay, so obviously the main measurement we've been playing with so far is the standard basis measurement, or the computational basis measurement. Okay, so for example, if we want to measure in the standard basis, the projective measurement is none other than B equals to 0, 0, 1, 1. Okay, this is the case for qubits. If we're talking about C2, right? And of course, this generalizes to II if you want to talk about higher dimensional systems. So let's start at 0 and end at d minus 1, and this would be in CD, right? So you can generalize this straightforwardly. So that's how you model the operators for a standard basis measurement. Okay, I haven't told you, of course, why this works or how you extract outcomes of the measurements or probabilities. I haven't told you any of that yet, but this is first the basic mathematical object we need to write down to do all of that. Okay, so let's just do a very quick sanity check, right? This is one of the exercises, but I'd like to do it here. Let's verify that B equals to 0, 0, what I just wrote down, is a projective measurement on C2. Okay? So to be a projective measurement, what had to happen is that two things, right? Number one, well, three things technically. You had to be Hermitian, which these things are, because actually they're projectors, right? Which is the second property I needed. They're actually projectors, right? Because this projects onto 0, this projects onto 1. You're staring at their spectral decompositions, right? There's an eigenvalue 1 here, and same here. The only thing that's not immediately obvious, well, it is if you, of course, take a moment, but we have to verify this completeness relation, right? That the sum, if I add these two guys, I should get identity, right? So if I add these two, okay, this is identity. Okay, this is one of the things I said in an earlier lecture, that if I take the projectors, basically, if I sum the projectors onto any orthonormal basis, I always get the identity. Okay, and let's just verify this here in a very naive way. Remember that 0, 0 is just going to be this 2 by 2 matrix. Again, in general, I don't want you to do this, right? But here's an example when I'll do it just to really convince you using first principles, right? That this is this, right? And that's just identity. Okay, so the completeness relation holds. And this means that, of course, this is a valid projective measurement. Okay, good. So now I've told you what is a. So this is the what is a measurement or a projective measurement. That's what we just answered. Of course, the object is useless unless I tell you how to use it, right? So the next question is how to use B. Right? So how do I actually model a measurement using B? Okay, in particular, I want to know if I have a quantum state and I measure it, what's the probability of each of outcomes and so forth. Okay, so here's the answer. Suppose we have some quantum state, so we want to measure some state psi, and this thing just lives in CD. Okay, so I have some state in my lab, let's say, and I want to measure this thing. Okay, and I want to do it via measurement B. Right, so this is just going to be projectors pi I equals to 0 up to m, so there are m of them, and these are linear operators in CD. Whoops, there's a typo in the course notes here. This should be linear operators on CD. Okay. Okay, so the first thing we care about is, of course, when I do the measurement, what's the probability that I obtain a particular outcome? And so let me make a note here. What do I even mean by outcome, right? So the point is that, each index I is going to be an outcome. Okay, so for example, if up here, we projected onto, the basis 0, 1, then you have two outcomes, right? Either you project onto 0 or you project onto 1. So this is going to be a probabilistic experiment, and you'll get one of these. These are the events that are possible. Okay, so in this case, the possible outcomes are each of the, formally each of the indexes I, basically. Okay, so what is the probability of getting any particular outcome then? So the probability of outcome I is what? So this is the formula. I'm defining it this way. This is the way nature works. Okay, so it's the trace of, take my state, psi, and in principle, then the main thing I want to do is I want to project the state down this, I want to know what are the odds, basically, or how much of the weight of psi, basically, gets projected onto this. Okay, and so let me just erase this for just 1 second, right? In principle, the odds of this happening, right? Let's go back to the picture. So over here, right, when I projected psi down onto 0, 1, right? Intuitively, you would expect that, if this state psi was very close to 0 to begin with, then when I measure in the 0 versus 1 basis, with high probability, I should collapse down onto 0, right? I shouldn't hit 1. And so intuitively over here, when I talk about the probability of outcome I, it should depend somehow on the norm of the resulting vector, right? So, I'm very tempted to do this, right? To say something like this. It's a 2 norm of what happens when I take psi, and I see how much weight does it have along the component pi I, or in the subspace that pi I projects onto. So, but I'm not going to do that. And the reason why is because, so technically you could do something like this, but I want to be more general now. I want to slowly start brainwashing you into a more general formalism, which we're going to need in the next lecture, which is the density operator formalism. And I'm not going to write psi as a vector. I'm going to write it as an operator, right? And remember, when I do ket-bra, I get an operator. So this is my vector. Here it is, this guy and this guy, right? That's the same vector, and I did a bra-ket. And so the probability of getting a certain outcome, I'm going to write this way. Okay, remember, this is the trace operator, trace map, and what it does is it takes this matrix and it sums the diagonal entries on the matrix, or equivalently, we said it basically sums the eigenvalues of this matrix. Okay, so that is the probability of obtaining outcome I if I measure my state psi using the measurement B. Okay, and I could say just a bit more. I could simplify this slightly. So I can actually write this. Pi I squared psi psi. Okay, so why is this true? Take a moment. So what I did is I moved this guy over, right? And for that, I use the cyclic property of the trace. Okay, so that's why this is true. And now we could simplify one step further, right? So I could write this. Okay, and why was this true? Okay, this is just because pi I is a projector, right? And so by definition, pi I squared equals pi I. Okay, so this is kind of typically we'll write the formula. Okay, so the probability of getting any particular outcome is modeled this way. And you might think this is some really crazy looking formalism, but the truth is this completely captures classical probability theory. So you could always embed any sort of classical experiment, probabilistic experiment, into this formalism. Okay, so it's really just a generalization to the case where matrices are no longer diagonal. If everything was classical, then all the matrices involved, including the projectors, would just be diagonal matrices. We would just have zeros in the off-diagonal. In a quantum world, though, it turns out you could work in other bases. And so that's why we write it in this more general way. Okay, good. So let's do our first exercise on this, right? So let's do an example, right? Let's measure our first quantum state. So suppose I want to measure this single qubit state, alpha 0 plus beta 1. Okay, it's a unit vector. Okay, let's measure in the standard basis, b equals 0, 1. Okay. Sorry, linear operators on C2. Okay, so let's figure out what is the probability of getting each outcome, right? And intuitively, again, if you stare at this thing, right? If you stare at it, if alpha is very close to 1, if most of the weight is here, you expect that when I measure in this basis, I should be getting outcome 0 with high probability, right? That's the intuition we're going for moving into this. So let's do the math, right? The math says the probability of outcome 0, meaning, ket 0, is equal to the trace of, and in fact here I'm going to write it, let me write it this way. So the projector, remember, is ket 0, right? That's the outcome I'm looking for. This is my state psi. And I think it'll be a bit easier, in fact, if we just use this formalism rather than the simplified one. Okay, so I have this thing, and here I'll put 0, 0 again. Okay, so that's what this is equal to. And now stare at this for a second and convince yourself that if I project this thing down onto 0, 0, now, this term, of course, dies off because it's orthogonal. So all I'm going to get left is basically this 0 term. So what does that mean? That means that, when I do this thing here, I'm going to get alpha times 0 on the left. Okay, and on the right, it's the exact same thing, right? I just have to take a dagger. So I'm going to get ket bra 0, and remember, I'm taking a dagger, right? So that means that I have to put a star here, right? Complex conjugate. Okay, so this is what I get. Now, the alphas are scalars, so I can pull them out. So let me do that. So I get alpha alpha star times the trace of ket bra 0. Okay, and there are two things I can simplify here. So take a moment and see if you could identify one of them. Okay, so remember trick number 1. I don't want you to forget this, right? This thing. This can always be rewritten alpha squared, absolute value of alpha squared. And over here, I can use the cyclic property of the trace to move this over and get an inner product, right? So this is nothing other than the inner product of 0 with itself. At this point, I could remove the trace because, this thing is just a scalar, of course. And 0 is a unit vector, and so that inner product is 1. Okay, and so I get alpha squared. Okay, so as you expect then, the probability, what is it saying? Let's take a step back, right? The probability of getting outcome 0 is nothing other than alpha squared, okay? So the larger alpha is, the closer it is to 1, the more likely you are to see that outcome, right? And the probability of now getting outcome 1, I'm going to leave you to do this computation on your own. This is going to be analogous, right? It's just beta squared, okay? Okay, so now now we come across, we have to take a step back and look at the big picture. Okay, now I have to see, why did we define things the way we did? How do the pieces fit together, right? So if I measure my state alpha equals to, psi, which is alpha 0 plus beta 1, the probability of getting outcome 0 is alpha squared, and the probability of getting outcome 1 is beta squared, right? So remember now I was really clear that we have to define a quantum state as being a unit vector, okay? So why was that important? Now it's clear why this is important, right? So note, the fact that psi is a unit vector, what did it imply? Right? It implies that alpha squared plus beta squared is equal to 1. Right? That was the exact property it gave us. And that is now super important, right? Because the two outcomes I could have had were alpha squared and beta squared here in this experiment, and they better sum to 1, right? Otherwise, it's not a valid probability distribution. Okay, so this means that the measurement yields a valid distribution. Okay, so this is why in quantum mechanics we want our state vectors to be unit vectors. Okay, because then measurement makes sense, basically. Okay, and the other thing, of course, is it's kind of obvious, but let me take a moment to point it out, is that quantum mechanics is inherently probabilistic, right? There doesn't seem to be anything we can do about this, at least if you interpret it in the Copenhagen interpretation, literally, right? So there's always some probability of an outcome occurring, and really there's no control you have over that a priori. Okay, now I told you what is the probability of getting a particular outcome when we measure psi. And the second thing left, which is completely trivial when it comes to the classical world, is what is the state of my system after I do the measurement, right? So classically, if you look up, let's say, what are the bits in a certain variable in Java, right? I mean, once you look them up, the state of those bits does not change, right? Quantumly, this is not true. Okay, so now we have to be a bit more formal and talk about the post-measurement state. Okay, what is the state after I measure? So question, what is the post-measurement state? Okay, and now we're going to use the fact that we're talking about projectors, right? Our measurement, there's a reason why we chose a projector, right? And that's because a projector, pushes the state down into some subspace, right? And that is going to tell us exactly what our post-measurement state is, of course. Okay, so let's formalize this. So formally, so first let me write, in English. So if we get outcome pi I, right, that's some projector, we project onto, let me not say we project in general, but we project psi onto the space pi I. Well, onto the support of pi I, basically, right? The space on which it projects onto. Okay, so let me be formal. So formally, okay, so psi collapses. This is the terminology we'll use. Collapses to some state. And again, I'm going to use this density operator formalism. Ideally, what I want to do is this, right? Let's be clear. I want to take psi, and I want to project onto pi I. Right? Now, I just said that, quantum states have to be unit vectors, right? And we saw earlier that when I project something down, I'm throwing away part of the state, so it's not going to be a unit vector. So I'm going to have to renormalize this thing to talk about a valid quantum state. Okay? And the naive way of doing this, again, would have just been to say pi I, psi, 2 norm. Right? You divide through by the norm, and now you get a unit vector. But I'm not going to do this, right? Because again, I want to get you slowly, I'm deviously trying to get you guys into the density operator formalism, which is what we'll talk about next class. So instead, I'm going to write things in the density operator format. Again, I haven't formally defined density operators, and don't worry about the definition yet until next class. So I'm going to write it instead as the bracket of my state, my projected state. And the renormalization, technically it should be this, right? It's this thing. When I do this, it's the 2 norm, but now I have 2 copies of the vector, right? Bracket, so I should put a square here. And if you expand this out and look at it closely, you'll see that this is really nothing other than this thing over here, the trace of pi I, psi, pi I. So it's more or less exactly what you expect, basically. The trace here of this operator is basically the normalization in operator world, right? Instead of taking the 2 norm, we take the trace, and it tells us the normalization, quote unquote. Okay, and again, if I want, I could always rewrite this as just the trace of pi I, psi. Okay, sometimes it's nicer to write it that way. Okay, so in the notes here, I'm trying to clarify some things about this expression here. So one of the things is, why did I write this thing in this operator formalism? And yeah, again, because we're trying to be devious here and slowly brainwash you guys into thinking in terms of, brackets of these states, because we're going to go into that formalism next lecture. But that's all I want to say for the first motive. The second motive in the notes is exactly what we said, which is this normalization, right? That's why this denominator is here, basically. And if you really want to be very precise, right, what we could write, because my state is a unit vector in this case, I could always rewrite this in this way. Okay, let me be a bit more, let me try and stick to my notes a little bit. So if I wanted to, in the pure state formalism, okay, so meaning i.e. not density operators, okay, what I would write is that we collapse to psi prime, and remember I told you this is just pi I psi, and this just equals to the 2 norm of the state, right? And if you stare at this long enough, you'll see that this is nothing other than this. Just to apply the definition of the 2 norm, remember the 2 norm is the square root of psi of pi I psi, okay? And I've cheated here. I've skipped the step. See if you could figure out what's the step I skipped. But this is the another way of writing the state if you just want to think about the pure state version. Okay, that's the pure state analog. Okay. Good. And so that's what happens when I measure. That's the post-measurement state. Okay, so let me just do a sanity check. And so we measured this, our state alpha 0, beta 1 in the standard basis. And now let's just check that if I get, say, outcome 0, I really do project onto the state 0. Okay, so let's do that sanity check. So exercise, this is one of the exercise notes. Let psi equal to alpha 0 plus beta 1. And B will just be this measurement in the standard basis. Okay, and suppose we get outcome I equals 0. Okay, so we project onto standard basis 0, state 0. Okay, so now let's see what the post-measurement state would be. So the post-measurement state is what? Well, we said first that happens with probability alpha squared, right? The post-measurement state now would be, if we use this formula, let's just stay in the pure state world. It's just going to be the projector, 0, 0, right, against our state psi. And then we have to renormalize this thing, right? So psi, and then multiply by 0, 0. Or maybe I could use brackets. It's a bit nicer, this thing. Okay, so that's just plugging in, this formula here. Yeah, this one over here. Okay, and so what is this? When I project this state over here, right, down onto 0, remember it kills off the 1 component. So that's nothing other than alpha 0, right on top on the numerator. And the denominator is what? Well, same thing, except now I have 2 copies of this, right? I have this thing here will just give me, well, technically it's just going to give me alpha, right? So, okay, let's be a little bit more careful. So this thing will give me alpha, right? And on the left-hand side, that's this one. And this inner product, these are both inner products, so I'm going to scalar out. This one will give me alpha star. Okay, so what I'll get is I'll get alpha 0 over the square root of absolute value of alpha squared, right? And then, of course, what is that? Well, that's just going to be basically alpha over the absolute value of alpha times 0. Okay? So it's not exactly 0, right? But remember, from an earlier lecture, we said that, this thing in front, this is a scalar now, right? This is just something in the complex numbers. This is a unit complex number, right? I've normalized it. Here it is, right? It's alpha, whatever alpha was. Didn't have to be norm 1, but I just divided by its norm. So this thing now sits on the unit circle, right? It's a phase now. It's like, this is just some e to the I theta, right? For some theta, okay? So that means that for all intents and purposes, as far as measurement is concerned, we're not going to be able to detect this, right? Our state is basically equivalent to the state 0. Okay, so you can think of this as one big equivalence class if you like. Okay. So by the way, this is a nice exercise. I don't know if it's in the assignment, but it's a nice exercise, and I'll leave this to you, is just to do a sanity check that this is actually true. I've said over and over again that if you have a phase in front of a state, the measurement can't see it. Okay, so now you have the tools to prove that to yourself. So as an exercise, show that for any projection, for any orthogonal projector pi, right, the probability and any state psi, right, okay, the probability of getting outcome pi, right, against psi, right, this thing, equals to the same thing. Oh, okay. I'm going to give away the answer if I write out the formula. It's really that easy. So let me not write out the formula. Let me make you write out the formula on your own. Okay. Show that the probability of measuring pi is the same. Okay, and let me say also for all angles theta in the reals, right, is the same for psi versus e to the I theta psi, for whatever phase you want. Okay, so if I take the state psi and I project onto pi, like that's some outcome, the probability of that outcome, right, if you just plug it into the trace formula that I just erased because it was giving away the answer, you'll very quickly see that these two guys have the exact same probability of that outcome happening. And also if you stare then at the post measurement state, you'll see that they'll be the same basically up to phase. Okay, so I did not lie to you in the previous lecture. Okay, good. So the next thing I want to talk about is it's still these measurements, right? But we talked about projective measurements. So why projective measurements? Why didn't we use, say, PSD operators? And by the way, you can talk about PSD operators for measurements. There is a notion of a positive operator valued measure. But again, those can all be simulated using projective measurements. So, but why are projective measurements the right choice of measurement in quantum mechanics? Okay, so here's another question. So again, life lesson, right? Whenever you're doing something advanced, something technical, you really want to ask the big picture basic questions, right? You guys are scientists, right? And so the obvious question is, why projectors? Why does the theory work this way, right? I mean, so we already saw that, unit vectors are necessary because they make sure that the measurement experiment induces a proper distribution. But now let's ask, what is it about projectors? Why projectors? Like, why does this make sense? Okay, and the answer intuitively is kind of sitting right here. It's this idea that, if I apply the measurement twice, right, if I do pi squared, I get pi back, right? So intuitively, what this is sort of saying is that if I measure something twice in a row, I should get the same answer, right? So think about it this way. If I had a quantum state in the lab, right, and if I were to measure it once and I got one answer and I apply the exact same measurement, like immediately right afterwards, like before, any sort of noise can creep into my system or any other unitary on the system can take place. If I apply the exact same measurement twice, I should get the same answer back. If that wasn't true, then the world we live in would truly be la la land, right? I mean, it just wouldn't make any sense. everything would be just completely random, right? So it turns out that projectors make sure that, we can maintain our sanity, right? That if I do the same measurement immediately twice in a row on the state, I'll get the exact same outcome, right? The state, it'll change the first time I measure it, but after that, the state will be consistent with what I measured. Of course, if in the meantime between measurements you have something like noise coming into your system, of course that can induce a further change on your system so that when you do your subsequent measurement, you do see another outcome. That's a different story, right? Here I'm really talking about immediate subsequent measurements. Okay, so ensure that if we measure psi repeatedly, and this is immediately, right? No intermediate operations allowed, we get the same outcome. Okay, and let's just formally, of course, see this. Okay, so let's suppose, formally, I have some measurement B. Okay, so I'm measuring in some basis psi I. Okay. And let's suppose now that I do two measurements. Okay. So in experiment 1, I get outcome I. And experiment 2, I get outcome J. Okay, where I does not necessarily have to equal to J yet. Okay. And now let's work out the math. Let's see what is the probability that if conditioned on having gotten in the first experiment outcome I, what is the probability that I'm going to get outcome J? Okay. So what is the probability that I get outcome J in the round 2, given that in round 1 I got outcome I? Okay, so what is that? I'm just plugging my formula, right? So first what I do is, what is the post-measurement state after I got outcome I? Let's write that down. Right, so remember what I said? This is psi. I project it onto pi I because that's the outcome I got after my first measurement. And remember then I write it in this so-called density operator formalism. And I renormalize because it has to be trace 1. Okay? After measurement I, this is the state after measurement I. This is my state. Okay? And now this is the guy I want to now plug into my next measurement outcome. I want to say that what is the probability of this thing collapsing onto the space pi j projects onto, right? So here's my pi j. Okay, so this is the formula. So again, this is my input state, right? This one here. And this is now my next measurement outcome. Okay. So what is this? Okay, well, maybe just write it this way, like in the notes, again, to be precise. So here I'll have pi j times pi I on the left, psi psi, pi j times pi I, right? And then I'll have this normalization factor in the bottom. Okay, and so here we're going to use the completeness relation. Okay, I haven't really told you this, but a direct consequence of the completeness relation is that these are two operators that are coming from the same measurement, right? And because the sum of these guys have to be the identity, that means that these guys can't have any overlap in some space. So they really have to be projecting onto disjoint subspaces. Okay. So that means that if I multiply two of these projectors, pi I and pi j, their product should also always go to 0 unless j equals to I, of course. Okay, in which case you get the same operator back. So here's an observation, and I won't prove it, but this is a nice exercise. So due to the completeness relation, which said that pi I squared for any I, let's not do that. That's not the completeness relation. The sum over I of I equals to identity of pi I. That's the completeness relation. We know that pi I times pi j is equal to 0 if I is not equal to j, and it just equals to pi I if I equals to j. Okay, so this is a very nice fact that we get out of this. Okay, and now when I apply that to this expression, you see exactly what's going to happen, right? If j is not equal to I, this thing's going to go to 0, and so the entire thing is going to go to 0. And so the probability of getting outcome j, having already seen outcome I once, that's going to be 0, right? Assuming j is not equal to I. So let me just continue this over here. So this is 0 if j is not equal to I. And otherwise, it's just going to be equal to, well, the same state, right? I haven't changed anything. So it's going to be the trace of pi I, psi, pi I, over the normalization, trace of pi I, psi. Right? And again, here I've used the fact that if j equals to I, then this thing is pi I squared, which is just pi I. It's a projector. Okay, and now just stare at this thing long enough, you'll see that the numerator is just the same as the denominator, right? So I can move, by cyclicity of the trace, I can move this over, and I just get trace over pi I psi all over the trace over pi I psi. Okay, and of course that equals to 1. Okay, this is of course assuming, so note how there's a slight caveat here, which is it's assuming that the odds of getting outcome I to begin with were not 0, because otherwise this is not well defined. Okay, but of course this entire experiment is conditioned on the assumption that I did get outcome I, so it must have had non-zero probability of occurring. Okay, so this is why we like projectors, right? It's because it allows us to be sane in our world, right? That if I make the same measurement twice, I should see the same outcome twice. Okay, that's it. So that's why we like projective measurements. Let me just close this section basically with the circuit symbol now of how we do measurements. Okay, so a circuit diagram for measurements. Okay, so what does it mean how do we depict this? I take my state psi, right? I've got a wire that's incoming, and the way I depict a measurement now is just simply this. This is one of the common ways to do it, and note how I will then draw these output wires in, I'll put 2 wires, and typically this just basically means that this is carrying now classical bits, or a classical bit. Okay, so 2 wires will just mean 1 classical bit. So I measured, and now my data is now classical in some sense. Okay, good. So that concludes our discussion of the measurement postulate. Okay, and now that we have that in hand, we can talk about quantum teleportation, basically. Okay, so let's now talk about the first application of measurements to a quantum information or communication task. Okay, so this is the task of quantum teleportation. So in quantum teleportation, right, there are going to be 2 parties, right? Let's imagine you're one of them. Okay, so there'll be 2 parties, right? One of these will be you. I'll let you choose which one is you, but of course they more or less look identical, so I might as well pick that's you, okay? And let's just call this other party Alice, okay? Standard names in the field are like Alice and Bob, Charlie. Okay, and suppose that you have a state psi in your possession. This is just some arbitrary state of a single qubit, right? And your goal is you want to send the state of your qubit to Alice, right? So what you want to do is you want to send this over to Alice. Okay, and you guys are spatially separated, okay? So you're not in the same room, so let's say you're living in different countries or something like this, right? So spatially separated. Okay, and so there are various things you could do, right? If I knew the state of psi exactly, like let's suppose I knew that the state psi was just ket 0, then, the easiest way to do this, of course, the cheapest way to do it using existing infrastructure is you just, pick up your phone and you're like, Alice, I have the state 0, and then Alice could prepare her copy of 0 on her side, right? And on the other hand, if you don't know what the state psi is, right? And you want to send Alice basically the state, right? One thing you could do is you could physically, put it in some sort of quantum mail, right? And just quantum email and just send it over to Alice, right? That presumably will be expensive and not easy to do. Okay, the other thing you could do is, of course, you could take your state psi, and since you don't know what it is, you can measure it. You can produce many copies of it and measure it over and over again. You can try and get some estimate of, what are the values of alpha and beta, right? And then you pick up the phone again and you call Alice and you say, well, my alpha and beta are approximately this, and she'll recreate it on her side. Okay. The problem with that one, of course, is that number one, you have to repeat this experiment many times. Number two is that it's only approximate, right? You'll never send your exact state to Alice. And, that's kind of, right? So firstly, this is really kind of a, sorry, let me put this back where it was. This is really a very non-trivial note here, right? That, idea one, and so let me, again, be clear that you don't know what psi is, right? Meaning, you have some lab apparatus is producing some state psi. You don't know exactly what psi is, right? And idea one is that you prepare many copies of psi. Measure each to estimate alpha. So you pick up some estimate that's approximately the right alpha, you pick up some estimate beta that's approximately the right beta, and then you call Alice on the phone. And what you do is you share alpha prime, beta prime, right? That's kind of the naive way you would do this, right? And like I said, I don't want to say the problem with this, but the drawback to this, one of the main drawbacks is that this is only approximate, right? So I get alpha prime, beta prime, right? I don't get alpha and beta. And intuitively, if you think about it, the expansion of alpha could require an infinite number of digits, right? It could be some irrational number. So in principle, it seems like there's no way you could transmit the exact state of psi from you to Alice. See, it seems like it should be impossible. And this intuition is actually false. Actually, you can do this perfectly, right? And that's part of the magic of quantum teleportation, right? It's kind of completely unexpected in that regard. There is a bit of a catch. The catch is, and we'll see in a second, is that to do teleportation, you first have to share a quantum state, a particular quantum state, the Bell state to begin with, between you and Alice. But that state itself, once it's set as a resource state, then you could teleport any other unknown state psi from you over to Alice. Okay, but let's get to that in a second. Okay, in teleportation, let me just make that note. So we can do the transmission of psi perfectly. Okay, but there is a but, right? There is a catch. I mean, it's too good to be true, right? But you and Alice have to pre-share a particular state, the Bell state. Okay, so remember that, and it doesn't really matter, of course, which Bell state you use. Remember, we said last lecture that there's a whole basis of Bell states for C4. So let me just pick this one. Okay, it's usually the one teleportation is described in. Okay, so as long as you guys share this kind of resource state beforehand, it turns out you could transmit psi perfectly with Alice, as long as you're also able to call her on the phone and discuss with her. Okay, so let me first just write down the circuit, and then we'll break down the circuit. So here's the circuit for teleportation. So here's the state. Did I? Okay, so my notation is maybe not matching what I'm saying here, but let's just follow the notes here. Let's just follow the lecture. So here you are, right? That's you. You have psi in your possession, right? And now you and Alice, you both share half of this Bell state, right? So, this is a single wire. This Bell state is 2 wires, right? Because it's a 2-qubit state. And what happens is the following. So let me be very, very clear here, right? This is you. You control these two wires, you. Okay, you have psi, and you also have half this Bell state, and this wire here, this is Alice. Okay? And so what happens here is the following. The first thing you do is you apply a control knot from the state psi onto your half of the Bell state. And again, let me be clear that, the spatial separation is here, right? If we think of this as, you versus Alice, right? You're at the top half of this. This is you in your lab, and this is what Alice sees. So in your lab, you're doing this local operation between your two qubits. That's why I'm saying this. It's a local operation for you. It does not touch Alice's space. Then you do a Hadamard. Okay, and then you measure both in the standard basis. Remember, this is the measurement symbol. Oops. Okay. And now we get classical bits out, right? Now that I've measured classically. And now you've measured your state, so you've kind of destroyed what's quantum on your side. But the magic of it is that what was on your side now, through the entanglement of the Bell state, right? We're sharing this Bell state. Through the entanglement of this, remember that this is in some way coupling these two wires in a very, very strong sense. The psi, this measurement we'll call psi essentially to jump over to the other side. Okay, and we'll talk about this more towards the end. But basically, Alice more or less has psi at this point. The only thing is that she might need to apply some conditioned corrections. Okay, so let me just draw this, and then we'll specify what this means in a second. Okay. Okay, so what are these things in the diagram? So this is a control knot, right? This is the Hadamard. These are measurements in the standard basis. This funny thing here is just a controlled X and a controlled Z, right? Just like a control. So this is basically a controlled knot, for example. This is the same thing, but a controlled Z. It only applies the Z operator if this control bit is a 1. And in particular here, there are two wires. So this is really classical gate in the sense that the control is classical, right? So it's either 0 or 1. There's no superposition on this control register. Okay? So what this is really saying is the following, right? Let's break it down into steps, time steps. Okay? So at the very beginning, we apply the C0 gate, right? So here, let me break it into time steps this way. So here, this is step 1. We apply the C0 gate. Right, in step 2, we apply the Hadamard gate. This is step 2. In step 3, you measure your first 2 qubits in your lab. Okay. Then in step 4, what happens is that you pick up the phone and you tell Alice, look, when I measured the second qubit over here, I got, let's say, bit 1. Okay, and if you got bit 1, then Alice on her side, she says, okay, I'm going to apply the X operator on my qubit. And if you got bit 0, then Alice will not apply the X operator on her qubit because it's controlled X. Okay, and same thing in step 5 for the controlled Z operator. Okay, so again, for clarity, for this one, for example, it applies Z if and only if the control bit is 1. Okay, if it's 0, then we do nothing. And again, the control bit is classical. Okay, so what is the intuition here, right? The intuition here, well, okay, it's kind of hard to see right away. I mean, we'll talk a bit more about the intuition towards the end, but the point here is that first you're doing some local operations on your end, right? Here's the C0 and the Hadamard, and then you're doing some sort of measurement, right? And then you pick up the phone and you call Alice with your measurement results, and then she does some local corrections on her side. And the claim is that over here, psi is supposed to pop out. Okay, and not only will it pop out, but it'll pop out perfectly, exactly, okay, with 100% probability. Okay? So let's do the analysis to see that, this actually works, and then maybe we'll talk a little bit more about some of the sneakier things that are at play in this picture. Okay? Okay, so for the formal analysis, I drew kind of 5 steps in this picture, right? So, formally. So let's let psi I denote the state of all qubits. Okay, so both U analysis system. Okay, this is immediately after step I. Okay, so immediately after step I. And now we could write out all this. Okay, so in the very, very beginning, right, over here, if I say psi 0, this is just the initial state, right? This is just going to be what I have over at this point, right? At this point in time. So the initial state is what? It's, well, psi on the first qubit, right? And then on the second 2 qubits, you've got phi plus. Right? If you want to, it might be easier the first time you do this to label these guys, right? I could put a 1 here. Let me not do that. It's easier to see, I think. Say just one color. 1, 2, and 3. Okay. So you have 1, 2, 3, right? And then where are we? Yeah, okay. So then the reason why I'm doing this is because you might want to just, to be clear, we could say that this is on qubit 1 and this acts on qubits 2 and 3. Okay, so a lot of times it's nice to put these subscripts just to be clear what's acting on what. But sometimes in the name of brevity, we'll kind of omit it. Right, and remember that your state, the first state is this on qubit 1, right? And on the second and third qubits, we have this shared state, 1, 1, right? So this is on 2, 3. Let me close the bracket. Okay, now I could expand the whole thing out. Remember, the tensor product allows me to do this. So first, this 0 pairs up with this pair of zeros, right? So I'll get alpha. So first, let me just factor out the 1 over root 2 to make life easy, because there's 1 over root 2 on everything now. So alpha pairs with the 0, 0, 0, right? That's just this guy. And then we'll pair these two together, and we'll get plus 0, 1, 1. Sorry. 1, 1, and that should have been black. Okay, and then I get 1, 0, 0. And sorry, I'm missing some alphas and betas. I'll put them in a second. Plus 1, 1, 1. Okay, I forgot to put the alphas and the betas. So alpha, alpha on the first 2, and I get beta, beta on the second 2. Okay. Good, so that's just the initial state. And the reason, why am I writing it this way? Why am I expanding the whole thing out in the standard basis? Well, the reason why is because all of these gates, right, the C0, the Hadamard, the measurements, all of them, we know their action in the standard basis, right? That's how we usually describe these things. So if I write my state out with respect to the standard basis, by linearity, I know what each of these gates does to each of these individual kets you see here. Okay, so then I could just follow the computation. So that's usually the trick you need to write down and follow these computations. Okay, so now after step 1, that's psi 1. What happens after I apply my first controlled NOD here? Right, so what state do we have? Well, it's going to be essentially this thing, right? But, and let me be clear, this is on all 3 qubits, 1, 2, 3. But condition on the first qubit here, right? It's going to decide whether or not to apply a C0 onto the second qubit. So what am I going to get? I'm going to get 1 over root 2 again. And the first guy does nothing because the first qubit is 0 here. Same for the second term. The third one starts with 1, so it's going to flip the second qubit. And again, here we're going to flip. Maybe I'll do these guys in red to be clear. This is flipped, right? So this flips to a 0 now. Okay, so that's what's changed. Okay. And now we're going to apply the Hadamard gate, this one over here. Okay. So this computation is just a little bit messier, but in principle, once you get the hang of it, it's simple. So the Hadamard is being applied to the first wire. So that means that intuitively, this first wire is going to go from a, remember, Hadamard takes 0 to a plus state. So first, let me just write it this way, just to make your life a bit easier in following it. Okay. Okay, now, again, I want to keep things in the standard basis because I know exactly how these gates act in the standard basis. So I'm going to have to expand these plus and minuses out. Yay. Okay, so, the first step, well, okay, each of these pluses and minuses is hiding a 1 over root 2 factor. So let me just immediately take that out, actually. And then this becomes just 1 over 2 because I have 2 copies of 1 over root 2 hanging around. And then here I'll have 0 plus 1, 0, 0, right? That's just coming from the plus state. Plus alpha, 0 plus 1. plus beta 0 minus 1. Okay, apparently I've decided just to forget parts of my state. This is a 1, 1. Okay, 1, 0 plus beta 0 minus 1, 0, 1. Okay, and now I can simplify further, right? I can just expand out the bracket some more. So let me do that. Well, actually, I'm going to skip a step because just again in the name of sanity. Okay, and what I'm going to do is that you can expand this out, and then you'll get one more step, and I'm going to skip one step. I'm going to expand and then refactor, basically in the following sense. So here, you see I'm doing a measurement, right? After step 3, so this is after step 2, right? After step 2, here's the Hadamard, and I'm about to do a measurement. And this is measuring in the standard based on these 2 bits. So in order to understand what's going to happen at this point, when I measure this state here, okay, when I measure the state here, I want to factor out the first 2 qubits. So I can see what string is there, 0, 0, 0, 1, 1, 0, 1, 1. And then I can tell which branch the computation will collapse into. Okay, so let me just draw the state. So I claim you could rewrite it this way. I encourage you to do this on your own. So you could extract out a ket 0, 0. Let me even write it in a different color because I think it'll be easier to see them, right? So you can factor this out, and then you'll have alpha 0 plus beta 1. And let me be clear, right, that this is now on qubits 1 and 2. This is on qubit 3. Okay, and now here I have 0, 1. Maybe I'll just do them all like this first. Okay. And this one here is alpha 1 plus beta 0. So 1, 2, 3. This one is alpha 0 minus beta 1, 1, 2, and on 3. And last but not least, we have alpha 1 minus beta 0. Okay, so if you stare at this long enough, you'll see that you can expand out this expression like fully, and then you could factor out the first 2 bits, and this is the expression you'll get. Okay, so why am I writing it this way again? The reason why I'm writing it this way is because I'm about to measure qubits 1 and 2, right? I'm right here, right? I'm about to measure these 2 guys in the standard basis. And the standard basis has 4 outcomes, right? It has 0, 0, 0, 1, 1, 0, and 1, 1. Okay? And when I write it this way, it's very clear what the 4 branches of the computation, right? This is the 0, 0 branch. When I measure and I get 0, 0, this is the branch I'm going to collapse into, right? Because these guys are the other outcomes, 0, 1, 1, 0, 1, 1. Each of these is an orthogonal branch. So when I hit this thing with a projector onto, say, 0, 0, the outcome 0, 0, these last 3 branches will die out, right? And only this one will remain. Okay, so when I write it this way, it's very clear what's going to happen when I do the measurement now. Okay, and so let me be a little bit clear. There's an exercise here. I won't do the exercise. We'll leave that for the tutorial. But how do you model the projective measurement onto the first 2 qubits? For clarity, right? It's the first time we're doing this. So I want to measure qubits 1 and 2 in the standard basis. So the measurement I use is what? Well, there are 4 outcomes, right? I have 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and these are on qubits 1 and 2, right? 1, 2. Okay, and you'll notice I left some space here between the commas, and that's no accident, right? This is supposed to be a matrix that acts on the full space, and this thing only acts on 2 qubits. I need to, write something else here to make sure that the operator I have really acts on all 3 qubits. Otherwise, it's not well defined, right? And what I want is, well, I want the measurement to do nothing on qubit 3, right? If we look at this diagram, the measurements only happen on qubits 1 and 2. Nothing happens on qubit 3 here. And so the appropriate way to model that is just with an identity on qubit 3, right? We're not touching it. We're not doing anything. Okay, and so this set of 4 operators, which is indeed a subset of linear operators on C8, okay, on 3 qubits, this is going to be our measurement. Set of measurement operators. You can check that these things do add up to the identity. Okay. Okay, so in the exercise, you'll show that, for example, the probability of getting any particular outcome, there are 4 here, right? And if you stare at them, what are the odds of getting any one particular one? Well, where's the amplitude? The amplitude's right here, right? They all have the exact same amplitude, a half, right? A half squared is a quarter. So each of them has a probability, the same probability, a quarter of occurring, right, intuitively. And in the exercise in the notes, which we'll probably do during tutorial, you're asked to actually show that the probability of, say, getting outcome 0, 0 here is going to be a quarter. Okay, so now the probability, so a post-measurement. Okay, so this is going to be a step. This is going to be after step 3, right? This one here, right after we measure. After step 3. Okay. So what's happening here is that, I measure, right? And when I measure my state, what happens if I get outcome, say, 0, 0, for example, right? Then my state becomes what? What is my psi 3, if you will? My state psi 3 is going to be, you take this full thing, right? And you project the first 2 guys onto 0, 0, right? It's going to be 0, 0, 0, 0, tensor identity, right? On 1, 2, and 3, right? And against my previous state. My state at the end of the previous step was psi 2. It's this guy over here. And so if I multiply this thing by this projector here, the 0, 0 was orthogonal to these 3 green dudes here. So those are going to die off. And the only term that'll survive is this one, right? So what you'll get is going to be a half. Well, okay, let me be a little bit more precise because I have to worry about normalization, right? So this thing is proportional to, right? Because I haven't written the renormalization in the denominator yet. So it's a half times just the first term that'll hang around, which is 1, 2, and then alpha 0 plus beta 1. Okay? And so that's what the state is proportional to, right? That's what's consistent over here in this expression. And in particular, now, we should renormalize this, right? It's kind of easy, right, to read it off, right? So why is it easy? Well, this thing was a unit vector. Alpha squared plus beta squared was 1 by assumption. And now I take the tensor product, right? Tensor product basically multiplies out the norms, right? And this thing here, this is not a unit vector, right? 0, 0 is a unit vector, but I have this half, right? So all I really need to do to make this thing a unit vector is get rid of that half, right? I don't need to write out the full formula. So more accurately, I know immediately that this thing is just this. 1, 2, alpha 0 plus beta 1. Okay? Now that's a proper unit vector. Okay, and we can do the same for the other 3 outcomes. I'm not going to run through the computation each time. But depending on the measurement outcome, right, we're going to get a different post-measurement state. And this is why the communication now is going to be necessary. Okay, so on the first 2 bits, I got one of those 4 outcomes. And if I just stare over here, if I got outcome 0, 1, what's consistent with that is this, right? Alpha 1 plus beta 0 on 3. This one was alpha 0 minus beta 1 on 3. And this one was alpha 1 minus beta 0 on 3. Okay? Okay, and now what we see is, oh, that's what I wanted to fix right here. Okay, so now what we see is the following, right? That depending on the measurement outcome on your side, basically, so let's say you got measurement outcome 0, Alice's qubit is exactly the one you wanted to teleport, right? If you got 0, 0, if you were lucky enough, Alice gets exactly your state, right? So up here in this picture, as soon as you do your measurement here, if you get outcome 0, 0, then you immediately know that down here on this wire, on Alice's side, in her lab, no matter how far it is away, in principle, she's supposed to have your state now, okay? But of course, there are 4 outcomes, and in the exercise, you'll prove that all those guys have probability of a quarter of happening each. So if you get outcome 0, 1, Alice doesn't exactly get your state, but almost, right? She just needs to flip the 0 for the 1. Just apply an X gate. And so in particular, this says that if your second wire is a 1, you want to apply an X gate, right? And let's just check that this is what this is doing, right? So here's the second wire. If the second wire is a 1, then you condition and it applies an X gate. And that will correct the error on Alice's side. Okay, and finally, for the last one, for example, well, let me do 1, 0. In 1, 0, the zeros and the ones are in the right place, but you have a minus, right? We have to apply a Pauli Z gate to kick out a phase for this 1 and get rid of the minus to a plus. And so this says that, if the first wire on your side is a 1, you want to control and apply a Z gate. And that's what it's doing. If your first wire is a 1, it will apply a Z gate on, it'll apply a Z gate on Alex's side. Okay, and the interesting thing then is, of course, if you have the last one, then it has both an X error, 0 and 1 are flipped, and it has a Z error, right? So you want to apply both gates, and in particular, it won't actually matter in which order we apply it up to phase, right? So in this case, if both wires are 1 on your side, you're just going to apply both gates on Alice's side. Okay, so that's how this protocol works. Okay, so what does Alice do? She applies her gates based on whether you tell her you got 0, 1 in the first wire, and here we just use these formulas that basically say that if I have, for example, alpha 1 plus beta 0, right, this just takes you back to alpha 0 plus beta 1, right, and that was psi, for example. Okay, so that was this case over here, right, where we got this outcome. Right, and let me just skip one and let's do zx, right? If I do zx of alpha 1 minus beta 1, sorry, beta 0, right? That's this case over here, right? What is that? Well, that's just z times, first you flip the 0 and the 1. Sorry, x times, no, z times that, sorry. So the x flips those two, and now the z just gets rid of the minus sign. And then you're done. Okay, so in this way, Alice is able to recover her state perfectly. Okay, good. And so that's the entire teleportation protocol, right? That's really all there is to it. It's a little bit magical, of course, as with many things in quantum mechanics, right? I mean, why in the world should this work, right? And there is a sense in which, you can sort of reason this out in terms of entanglement theory. But let me just briefly note now, like something had to happen, right? There had to be a trade-off, right? So what is it? Like in Game of Thrones, for example, when the witch doctor brings the warrior back to life. Sorry, I forgot all the names, right? But she says, only life, only death can pay for life, or something like this, right? I mean, you have to give something up, right? And so what do we give up here, right? I mean, we have this magical thing happening where psi pops out on the other side, on Alice's side, right? But what have we lost in the process? Well, the resource state, right? We started with a Bell state between us, right? And what happened to the Bell state? Well, at the end, we know that, there is exactly psi here, right? And so what's on your 2 qubits? Well, what's on your 2 qubits is one of these four combinations, right? Depending on what your measurement was, you have a classical string, say 0, 0, okay? So you've totally killed that entanglement, you've used it up, but in return, you've quote-unquote teleported the state psi over. Okay, so that's the first thing we've done, right? Note. Oops. Oh, okay, never mind. So note 1 is we used up phi plus, right? And the other thing is that we did not create a copy of psi. Okay, well, so what did not happen here is it did not happen that, psi is here and I created a copy here. No, we're not allowed to do that. No cloning theorem of quantum mechanics says you cannot create copies of unknown states. Okay, so what necessarily had to happen by the laws of quantum mechanics is that your copy of psi disappeared, right? Now at this point, you just have a string here, right? It's only Alice that now picks up that copy of psi. So that's also very subtle and very crucial, right? So we did not create a copy of psi. Okay, and this is also why, you might want to think of it as genuine, in some sense, teleportation, right? I mean, you had to move psi over. You didn't just create a copy of it. Okay, So there's a sense in which, nevertheless, this remains quite mysterious, right? We could make a little bit of sense of this by moving into the final kind of topic for this lecture, which is, everything we've talked about so far in terms of measurement has been measuring in the standard basis. Why, right? What's so special about standard basis? Well, it turns out that without loss generality, we could always work in the standard basis for measurements. And the reason basically is because we could always imagine that before we do the measurement, we apply some unitary, right? And the unitary basically changes the basis from whatever basis we want to measure and into the standard basis measurement. Okay, so let's talk about that next. And that'll also give us at least some intuition as to, what exactly is happening in this teleportation protocol. So maybe I'll zoom in just a bit more. There. Okay. So now this is section 3. Simulating arbitrary measurements via standard basis measurements. Okay, so the idea here is very simple, right? So this kind of trick, if I think back to like my undergrad times, like it's used in graphics all the time. And if you are an expert in graphics, please, feel free to disregard anything I say as being not entirely correct. But, this is the basic idea. So suppose, I have some image, let's say, okay, and I know how to, I have two vectors, let's just call them cat0, cat1. And I want to do some sort of operation, right? Let's say I want to do a reflection, right? Reflections are a good one. So suppose I have something like this, right? So I have some state psi, right? In graphics, maybe psi would be like some object, right? Let's say some character in a video game, right? So if you want, you could think of a character in a video game, right? There he is. And now suppose that I want to reflect this character video game about the state, about this, the x-axis, right? I mean, so I don't have to call these, we don't have to think quantum, we could just think of them in terms of x, y, right? So I want the character to go, let's say, under the water, let's say, right? So I want to do this reflection, right? I want to move the character down here. Okay, so that's a reflection about the x-axis. But maybe I also want to do other reflections, right? Maybe I don't want to just reflect about the x-axis, but I also want to be able to reflect about this one, right? So maybe if some weird axis like this one, whatever that is, right? So I can think about this axis now. Right, this is another pair of axes. Let's call this x prime, y prime. And maybe now I want to, also be able to do reflections about this axis, right? Of the character. I want to be able to do both kind of reflections, right? But I don't want to have to worry about, for each possible choice of, axis, having separate code, let's say, for doing the reflection. So one easy way to do it is, it suffices just to know how to do this reflection, a reflection about 0 and 1, basically. If you could reflect relative to this set of axes, you can do any reflection. And the trick is simple, right? If I want to instead reflect about this set of axes, what I do first is I rotate the space, right? I take, I apply essentially a unitary operator. I mean, that's really what it is. It's a rotation matrix. And what it does is it will first map this axis onto the 0, 1 axis. I'll first map myself into the 0, 1 space. And in the 0, 1 space, I know how to do my reflection about 0, 1. I'll do it. And then I'll just rotate everything back. Okay. So this picture's gotten a bit messy, right? Okay, let's see if I could quickly sketch what it would look like, right? So here's my thingamabobber. There's the axis I want to reflect about. Okay, let me draw my dude. So let's say that's my dude. Okay, so what do? I first rotate this thing onto the x-axis, right? And what that means is that, of course, that rotates the whole space. So this guy would rotate here. Okay, and then I would have dude prime over here. Okay, and now I know how to do the reflection about the x-axis, right? So then I do the reflection. So he then gets reflected over this way about the x-axis. So he'll be something like this now. Do double prime. And now I undo the rotation, right? I go back to whatever this angle was, right? So whatever this angle is here, I want to undo it basically, right? So my dude here is going to now go up. Whatever this theta was here, now he's going to go up theta degrees. Okay, and finally I'll get ultra dude, right? Dude triple prime. Okay, and that's exactly kind of what you'd expect. If I had taken this guy and reflected him about the red x-axis, I would have gotten exactly this one. Okay, and this is exactly the idea of how you simulate measurements using standard basis measurements, right? If I have any other basis, I first do a unitary, which corresponds to this kind of rotation of the axes. I measure in the standard basis, which I know how to do, and then I undo the rotation to go back into, to get the answer I really should have gotten. Okay, and now we can formalize all this. Okay, so this is just based on the fact that, you know, when I defined a measurement in the picture formalism, right, in the gate formalism, you know, this thing was always standard basis. I never said, oh, we can measure in whatever projection. Remember the measurements are projectors, right? They don't have to be in the standard basis. But my picture only allowed standard basis. Okay, and so we actually proved this last class, so I'm not going to... Okay, so here's the formal lemma. Lemma 1. Okay, so let B1 just be equal to some basis, right? Be an orthonormal basis. Then for any unitary U, which is a linear operator acting on CD, this thing here, U psi I, from I equals to 1 up to D, is also a basis. Okay, it's an orthonormal basis. Okay, so again, we did the proof last class, so I'm not going to do it again here. But basically what this tells us is that unitary operators do two things, right? They preserve norm, because you still get an orthonormal basis, and they preserve angles between vectors. Okay, and as a result, they're just rotations in space. You should think of them that way. Okay. Okay, so by the way, if you look up like Wikipedia or whatever, and you go to like a rotation matrix, right, and we go back to this picture, typically what you'll see is something like this, right? If you're working in 2D, the rotation matrices will look something like this. I mean, forgive me if I get this slightly off, but you know, it looks something like this, right? You've got coses and sines, and okay, and if you stare at this long enough, you'll see that in fact this is a unitary operator, right? I mean, the inner product of these columns will be yeah. So the columns of this matrix are basically an orthonormal basis if you stare at it long enough, and so you can convince yourself that this is unitary. But of course, everything's real in this picture, so then it's just a rotation matrix. Now, in our case, of course, we have complex entries, and so we don't just have like these real symmetric, rotation matrices. We're going to have unitary, more generally, unitary matrices, which allow complex entries. Okay? Okay, seriously need to stop doing that. Okay. Good. Now, there's a really neat trick I do want to mention. Okay? Very, very, very worth keeping in mind. So, neat trick. You know, in principle, this should make you happy. In principle. So if you have any pair of bases in mind, okay, so for any B1, right, and B2 is just, let's just call it phi, right, and these are both going to be just living inside, say, CD. There always exists a unitary which maps. So there's a unitary which acts on the space, CD, and it does it in maps, mapping, I wanted to say, B1 to B2. Okay, so basically what does that mean? It means, for example, that U times psi I equals to phi I. Okay? And not only that, it's trivial to write down the definition. Here it is. Okay? So do keep this in mind. What do I want to do? I want to take psi I, right? And I want to map it to phi I. Okay? So I write this bracket down. Now this is a funny looking thing because it's certainly not Hermitian, right? But this is, I can write it. It's a well-defined object, right? Well-defined matrix. And if I sum over all the possible vectors I, it'll turn out that this is the unitary you want. Okay, so I'll leave it as an exercise for you. So check that U is unitary and that it does this mapping, okay? But that is the trick. Okay, so for any pair of bases, you can map between them using an operator written this way. And this is another testament to the power of the bracket notation, right? It's very, very nice and easy to write this operator down. I don't have to write out any explicit matrices to do this. Good. So let's return to simulating a measurement in an arbitrary basis with standard basis measurements, right? So what do I want to do? So recall, what was our goal? Want to simulate a measurement in basis. And let's just assume we're talking about qubits here to make life easy. Psi 1, psi 2. Measurement in basis B by standard basis measurement. Okay, so what do we know? So by the trick, we know that there exists a unitary U such that if I apply U to psi 1, it maps me onto my standard basis vector 0, the first one. And if I apply it to the second vector of B, I get my second basis vector 1. Okay, so it aligns those bases. So there, the U is literally this rotation here, right? That takes this red initial axes and it just rotates them onto this XY axis, right? That's literally what this is doing. Okay. Okay, and now I measure, the resulting state, this one, this U psi in the standard basis. That's supposed to be the idea. Okay. So the circuit would be the following. First, you apply this unitary U, whatever that is, right? And well, you know a formula for it, by the way. So as a good exercise, see if you could write down this formula for U, based on, of course, psi I and 0, 1, right? You don't know exactly what psi I are. And then you measure. Right? You measure in the standard basis. Okay, and that simulates the measurement. Now, let me convince you, of course, you shouldn't just believe things for the fun of it, right? I should convince you that this is indeed correct, right? I see I've hit the bottom of this thing. All right, so let me convince you that this is indeed correct. Okay? Why does it work? Okay, so let's see. Well, so what is the probability of outcome psi 1? Let's just say, right? Suppose I'm measuring my state psi, right? And I want to know in this original basis B, what is the probability that I get this outcome, right? Well, remember that this is nothing other than the trace of, the projector onto psi 1, here it is, okay, times my initial state, which is this one. Okay, so this is my state, initial state. Oops. And this is the projector. Okay, and now I just told you though that psi 1 over here times U equals to 0, right? So in particular, of course, what this means is that this is completely equivalent. I can move the U over, right? I know the inverse of U. It's unitary. It's U dagger 0, right? And this thing equals to U dagger 1. Okay. So then I could rewrite this guy over here. The one on the left, the psi 1, psi 1. I know what it is. It's the same thing as saying U dagger 0, right? Just by this equation. And then I have 0, U. Okay. And then times psi psi. Okay, but now I'm almost done, right? Because now by the cyclicity of the trace, I can move this unitary over here, right? So I have the trace. What? I have 0, 0. And then I'm going to group this U on the right here. I'm going to think of it, instead of as applying on the left here, I'm going to think of it as applying on the right. I can completely do this. It's just matrix multiplication, right? So it's U psi, psi, U dagger, right? And what is this then? This is nothing other than the probability of outcome 0, like this thing over here, right? Given state U psi, right? That's literally what the formula is. Let me just maybe move this slightly up, right there. Oh, okay. Let's move it this way. Yeah, it's given the state u psi, right? So that's exactly what this is saying here, right? I mean, you might as well just apply u to your state psi, and then you have this state, and then you measure this state in the standard basis, and then what's the probability of outcome 0? Okay, it's completely equivalent. Okay, so finally, based on this, we can go back and visit, this idea of you simulating other measurements on other bases in the standard basis. With this idea in mind, we can go back now and try and make a bit more sense of what's happening in the teleportation circuit. So let's go back up. Where is our good friend, the teleportation circuit? There he is. Okay. So in the teleportation circuit, what I'm going to do is I'm going to single out a certain part of it, right? The standard basis measurement is here, right? And you'll notice what I've done is, of course, before that, I can think of these two guys together as a joint unitary, right? This is just, it's a sequence of unitaries, and the product of two unitaries is another unitary. Okay, they form a group. And so this is just some big unitary I can think of. And so what am I doing? I have some input state. I'm doing some rotation, some change of basis, and then I'm measuring the standard basis. Okay, so the question is, what basis am I measuring in? Okay, and stare at this for a second. You've seen this circuit before. Where have you seen this circuit? So this circuit here is the inverse of the circuit for preparing the Bell state, right? So recall, I'll just do this on the right here. Okay, recall that if I did this circuit, right? If I started with 0, 0, right? And then I applied a Hadamard and then a control not, right? Then this prepared the Bell state. And indeed, if I change, the input state to be one of the other three 2-bit strings, I would get one of the other states from the Bell basis. So this circuit here was just, like if I think of this as one joint unitary, U, right? This is just the circuit for preparing a Bell state, right? For converting the standard basis to the Bell basis. And this is the dagger of that, right? This is the inverse of that. So this is the circuit which maps me from the Bell basis into the standard basis. Okay, it goes the other way. So what measurement is this doing? This is simulating a measurement in the Bell basis. Okay, if I take this unitary U, there you go, and I think of it jointly with this is a measurement now in the Bell basis. That's what it's doing. It's measuring the input in the Bell basis. So something very interesting is happening here. There's a phenomenon known as entanglement swapping. And what's happening here is that these two guys are very strongly bound, these two wires. What you have half of and what Alice is half of. They're really tightly coupled together, and you have your state over here. And now there's this very funny property in quantum mechanics, which I won't talk about too much here, but called monogamy of entanglement, which says basically that if these two wires are very, very closely tied together, if they're entangled very strongly, then the third wire cannot be entangled with either of them. Okay, so it has to be in tensor product. And so what's happening here is that if you force these two wires to become a Bell state, because that's essentially what you're doing, essentially you're projecting into the Bell basis by doing this measurement, you're essentially going to end up coupling these two. If you're here, you're forgetting about, if you don't actually observe the measurement result, okay, then it would have the effect of projecting you onto the Bell basis, basically. And when you're on the Bell basis here, these two wires become very tightly bound. And so it must be the case that the third wire is decoupled by this so-called monogamy of entanglement. It can't be entangled anymore. So essentially you've swapped the entanglement from being on the second and the third wires to the first and the second wire. Okay, and so that's some intuition as to why the circuit sort of works. You're basically just swapping where the Bell state is. That's really what's happening, and the state psi kind of jumps to the last available wire, in this case the bottom wire. So at this point you would have a Bell state, basically, and then, it's like measuring in the Bell basis, and of course when you measure, then you're projecting onto the standard base. Now you're really destroying that entanglement. Okay, so that's one way of thinking about these measurements. Okay, and the teleportation circuit. So that's all I want to say about the teleportation circuit. The last thing we could talk about is just briefly revisiting Schrödinger's cat, right? So in Schrödinger's cat, remember in Schrödinger's cat, let me make myself some more space here rather than going all the way up, right? In Schrödinger's cat, what did we do? We said that you have a cat that's in a box, right? So here's your cat, meow meow. Okay, and in the box is a vial of poison. And then connected to this box was some sort of hammer mechanism, right? That is controlled by some computer outside, which looks like an Atari from the 1980s. Anyway. Yeah, and the idea was, remember, if you feed the bit 0 here, then nothing happens. And if you feed in the bit 1, then the hammer falls, the flask of poison breaks, and the cat dies, right? And of course, there's this question of, what happened if you fed in the input plus here, right? Which is 0 and 1 in superposition. And then that would say that the state of the cat inside the box is dead and alive at the same time. And of course, this made no sense. And knowing just postulates 1, 2, and 3, we couldn't really make sense of this at the time, at the end of the previous lecture. But now with the measurement postulate in hand, we can resolve the paradox, right? So how do you resolve the paradox? Well, I really stress that, I put a double border here because the box is closed. Okay, and what that intuitively means is that no measurement has taken place. Okay, now what happens when I open the box? Because in real life, of course, you would open the box to look at the cat, right? So if I get rid of this thing, and you want to know, should I laugh or should I cry? Is the cat alive or is the cat dead, right? Okay, so sorry, my whiteboard crashed for a second, so let's just continue. I had to redraw this, and so I apologize for the shift in the drawing. So let's very quickly wrap this up, basically. We were saying here how, I could put this superposition to plus, right? And so the cat could be both alive and dead, but now we open the box, right? And opening the box, right, then you're looking at the cat, and that looking at the cat corresponds to making a measurement, basically. So why is that? Well, how do you look at the cat again? You open the box, and so what does that mean? That means that light shines into the box, right? Which means, millions of photons, right, to shine in onto the cat. They bounce off of the cat, they return to your eyes, and they're processed by your brain, right? And then your brain forms an image of what it sees, right? So this entire process is what we refer to as the measurement, basically, okay? And when you do this measurement, as we've seen, you're measuring in the basis cat is alive versus cat is dead, right? You collapse into one of the two possibilities, right? So say cat is alive with some probability. And what we've seen, remember, is that the measurements are modeled by projectors. So if you look at the cat twice, you will see the same outcome. Once it's alive, once you see it's alive, when you look at it again, when you measure it again, you're always going to see that it's alive, okay? Unless, of course, there's some intermediate action that took place, okay? So this is how we resolve the paradox, right, of Schrödinger's cat, right, this measurement postulate. Okay, and again, I really don't want to get into any sort of arguments about interpretations. What does this all mean? This is all, of course, if you interpret quantum mechanics literally. And again, there's an entire field that devotes itself to studying different ways to interpret quantum mechanics. It's called quantum interpretation. So if you're interested, you're more than welcome to look up that literature. Okay, so that is it for lecture 3. And now we know all the postulates of quantum mechanics. Okay, and we've even done quantum teleportation. Again, I will shortly post assignment 3. If you have any questions, let me know in the meantime. There is a good chance that for the tutorial, I will get you guys to send me any questions you have ahead of time, because we might not be able to do it interactively. And maybe then I could also take up your questions in tutorial. So maybe that would be some, delayed interaction, if you will. Okay, that's it. So please have a good week, and as always, stay healthy.